We will continue with our lectures in this course on process control. In the last lecture, we talked about how to analyze closed loop systems. We basically showed that once you understand the structure of the transfer function and how to derive these closed loop transfer functions, then analysis of closed loop systems is not very different from analysis of open loop systems. We showed that in a typical open loop system, the output will be a function of the input and disturbance variables, and there will be transfer functions corresponding to the process and disturbance. Once we close the loop, we showed that the input itself becomes a function of the error, and as a result the input or the manipulated variable is not an input to this closed loop block diagram, and that would be replaced by y set point, and the disturbance variable will still be an input. So, the output will be a function of both y set point and the disturbance variable. So, this is what we had seen in the last class, and then we also described what are ideal transfer functions from viewpoint of servo control and viewpoint of disturbance rejection control. We showed that if the transfer function for the set point effect on y is very close to 1, then the output will follow the set point very closely, and if the transfer function which models the effect of the disturbance on the output is close to 0, then the output will be largely immune to the effect of disturbances. And then we also saw that these are not objectives which are counter to each other, and we showed that if we take very large control actions, then you could have both the transfer function with respect to the set point going to 1 and the transfer function with respect to disturbances going close to 0. So, now that we have looked at all of this, what we are going to do in this lecture is actually see how this works. We are going to take a very simple process transfer function, and then we are going to take these controllers as P, Pi, and then look at how these transfer functions look and what are general principles that we can learn from this exercise. So, you might want to think of this lecture as going to more details where we put in more structure to the controller transfer function and then see what effect it has in terms of the performance metrics that one would be interested in. So, let us start with a very simple first order transfer function. This is something that we had seen before. So, this is of the form k over tau p s plus 1. K is the gain of the transfer function, tau p is the time constant of this transfer function. Now, what we are going to do is we are going to assume that this is a process, and then we are going to see what happens if I control this process with a proportional controller, and then can we see some performance related computations for proportional controllers and see how well they behave. While we do this, we will also look at the disturbance transfer function. Let us assume that is also first order, which has a different gain k d and which has a different time constant tau d s plus 1, but nonetheless the form is the same. So, remember that basically what we are saying is that this y of s is g p u of s plus g d d of s. So, this is something that we have seen several times. Now, when we close the loop, we said this y of s will have a process related closed loop y set point of s, set point as input, and we are going to have a closed loop disturbance transfer function which is going to multiply d of s. So, this is open loop and this is closed loop, and we already derived how these transfer functions are going to look. We derived what the transfer function will be in terms of GP closed loop and the transfer function for GD closed loop. So, let us start with GP closed loop for controller, which is a proportional controller. Remember from before we said u of t is some kc times et is the equation for a proportional controller, where we said the effort that we take in controlling the process or the manipulated variable value that we keep is directly proportional to the error that is seen. Okay. So, ut is kcet, and this kc is the tuning parameter of a proportional controller, and the structure of the proportional controller then simply becomes Cs equal to Kc, because if I do a Laplace of this, I get u of s is C of s, E of s, and C of s is Kc. So, remember the closed loop transfer function form for Gp we said is Gpc divided by 1 plus Gpc. Okay. So, we substitute this here. So, that process transfer function is k over tau p, add the tau p here. Okay. So, k over tau ps plus 1 times kc Gpc. So, this is the Gp, this is the controller divided by 1 plus Gpc. Now, if you simply multiply this denominator by tau ps plus 1 on both sides, you will get 1 plus tau ps plus kkc, and in the numerator you have kkc. Now, this is the transfer function with respect to this here. So, which is what we saw from the previous class. So, if there are no disturbances and you are only looking at servo control, then y is Gpc by 1 plus Gpc, y set point s. So, that is going to be kkc divided by 1 plus tau ps plus kkc. Now, we have derived this. Now, what we want to do is we want to see how the controller behaves and how the output behaves whenever there is a change in the set point. Let us for example assume that I give a step in the set point. So, basically the picture that you want to keep in your mind is the following. So, I have y as a function of time, okay, and let us also say I have y set point as a function of time. So, initially all are deviation variables. So, y is like this, y set point is also like this. Let us say at some time I give a step in my set point. So, I increase the unit to 1. So, I say basically the set point suddenly changes. Okay. So, at this point there is an error between y and y set point, and because of this the control action will start happening. So, the y starts moving. So, this y movement is as a result of this y set point input. So, if I am going to give a step input in y set point, then from before we know that the Laplace transform of that is 1 over s. So, basically what I will get is this equation, y is k kc divided by 1 plus tau ps plus kkc times 1 by s. This 1 by s comes because I have given a step input to the set point. Now, ideally what you would like to do is have the controller set in such a way that after a while, clearly it cannot happen right away, but after a while this output reaches the set point. Okay. So, in other words, ultimately I want the output to reach a value of 1. Okay. So, y set point is always 1 because I have given a step, and then from then on it is remaining to be 1. Initially y will not be 1, but as the controller starts working, after a while you would want this y to go to 1. So, the final value of y should be 1. So, what we would like to do is we would like to check if the final value of y really goes to 1 or not, and from what we have learned from before, we can use what is called the final value theorem, which says if you want to find the final value of y of t, that is as t tends to infinity y of t, then that is given by limit s tends to 0 s y of s, and we already have the y of s here. So, what we are going to do is we are going to basically use this limit s tending to 0 s y of s is limit s tending to 0, here is s, and this whole thing is y of s from here. Let me add that tau p here. So, what happens now is that this s and s gets cancelled, then when you set s to 0, this term goes to 0, then you have this limit as kkc divided by 1 plus kkc. Now, you notice something very interesting here. You see that as t tends to infinity, ideally you want y to go to 1 because I have given a step of 1, and if it goes to 1, I would say the controller is working very well. However, you see that this can never be 1, it can approach 1, but it can never be 1, and as we said before, for it to be 1, essentially what you need to do is you have to keep pushing kc towards infinity. A larger and larger value that kc takes, the closer and closer this will become to 1. So, if you want very close to 1, you do not want any error, then basically that means kc has to be very, very large. Okay. So, this illustrates what people call as offset in proportional controller, which says that whatever you do with a proportional controller, there will always be a minor offset between the true value that you want the output to take and the actual value it takes. And the offset can be small or large depending on the values of k and kc, but for sure you know whatever be the value of k, which is the natural gain of the process, as long as you make kc larger and larger, this offset will keep coming down. But the problem with making kc larger and larger, as I mentioned in the last class, is that you will take unnecessarily large control moves, because for a small error, remember this, ut is kc times et. For a small error, if kc is very large, your ut is very large. So you do not want to do it. So it basically says if kc becomes very large, even if you have a minute error, your ut will simply shoot up, which first is not a good idea for control, and number 2, it might not be physically possible. So imagine that in our regular life we use taps to get water, and you can open the tap fully and there is a maximum limit of flow that you can get, you cannot get larger than that. So it is simply not physically feasible to get very large u values with standard control equipment. So that is a problem. So basically what we need to do is we need to basically live with this offset, and there are several processes where this offset is really not a problem, because if you are, let us say, maintaining the level of tank, water in the tank, you do not really want the level to be exactly maintained. It really does not matter, as long as it is in the ballpark, it might be good enough. So there are several systems where the proportional controller is very useful, because it is very simple. Tuning is simple, the structure is simple, it is just one constant, and it does not arbitrarily introduce oscillations and so on. So there are several interesting useful properties of proportional control: ease of implementation, simplicity, does not introduce unnecessary oscillations and so on. However, the negative is offset. So you will see in real plants several loops which are non-critical, but where you need simple control, you will see proportional controller. Okay. So the advantages are basically rooted in its simplicity and ease of implementation, and the disadvantages basically in the offset. Now let us see what happens for the disturbance transfer function. Let us say if I had d of s, remember we said this closed loop d times d of s. So the closed loop transfer function for d basically will be, we said gd of s divided by the denominator is the same, 1 plus gpc. So if you look at this and then you simplify this, you will get the following: kd divided by tau p s plus, okay, so kd. Now you will have tau p s plus 1 in the numerator, because in the other case tau p s plus 1 and tau p s plus 1 got cancelled. In this case, because tau p and tau d can be different, you will have this in the numerator, and this will be tau p s plus 1 plus kp kc. So this will be here inside times tau d s plus 1. So this is what you will have in terms of the transfer function between y of s and d of s. Now if you do the same thing and then say I am going to give a step in my disturbance, and then I want to see what happens. So basically here this is a plot between y set point and y, but for a disturbance, let us say if you have a different plot, let us say disturbance. So till here I have 0 disturbance, and suddenly if I have a disturbance, in this case you wanted the y to follow it, but in this case what you would want y to do is stay flat, but in real situations it will not stay flat. So what you want to do is whenever a disturbance hits, you want the y, maybe it will have to increase, but at least it has to come back to 0, because we want to reject the disturbance. So remember, these two pictures are very important. When there is a set point step, we want y to follow the set point. So we want the y to follow the step, but when there is a step in the disturbance, we want y to stay flat. So we want it to be 0 always, but there will be this minor thing. So ultimately if you do the same thing and then try and see what happens to limit t tends to infinity y of t when there is a disturbance, which will be equal to limit s tending to 0 s y of s, you will notice again that this will not go to 0, which is ideal, right. So which is what we want, it will not go to 0, it will be close to 0, but it will not go to 0, and again you will see that as you keep increasing the Kc value, the controller gain, you will see that you will go closer and closer to in this case. So, this I am going to leave it as an exercise for you to finish. It is very simple algebra that you do very similar to this and then see what happens. Okay. So, the upshot of all of this is proportional control is very good, and we have started analyzing the impact of proportional control on processes based on whatever we have learned. We have only used these two transfer functions that we derived in the last class. So, the transfer function between y and y of s is GPC divided by 1 plus GPC. The transfer function between y of s and d of s is GD divided by 1 plus GPC. Now, once you have your GP, GD and C is K, you can see that there will be an offset in my servo tracking, that is my output will not go to 1 ultimately, which is what I want, and there will be an offset in my disturbance rejection also. This is a case where I want y to be 0 as t tends to infinity, but that will not happen either. Nonetheless, because of its ease and simplicity, proportional controller is quite heavily used in the industry. So, the offset you might define as the difference between the desired and actual value. So, for that example that we had, the offset because I gave a step of 1, the ultimate desired value was 1, but the value that the output takes t tends to infinity y of t is kc by 1 plus kkc. So, this if you do some simple algebra, you will see that this is 1 by 1 plus kkc. So, this is offset from a servo control viewpoint. Of course, you could also do the same offset for the disturbance. Let us say if I gave a disturbance step and then I try to find what the offset is. So, in that case you have to say offset equal to what is the desired value for the output? The desired value for the output is 0. It is 1 in the case because it is a set point change and I want the y to follow the set point. In the other case, I have a disturbance step and I do not want the output to follow the disturbance, I want the output to stay where it is. So, that is 0, right, but whatever value it takes, okay. So, that difference if you take that as offset, this will be a negative number, but you can basically say this is the difference between what is desired and what I get, okay. So, you can find this as this minus 0 if you want. So, that is another important definition that people generally use. So, it would be worthwhile for you to do this computation and then see what happens. Now, while we talked about these performances in terms of final values, right. So, whenever I give a step change in set point, I want the final value to be 1, whenever there are disturbances I still want the final value to be 0 and so on. So, these are kind of metrics which are static or steady state metrics, right, but what we also want to know is dynamically what does the control do, right. It is not only a static metric that we are interested in. From the dynamics viewpoint, what is the controller doing is something that we might be interested in answering. So, what we are going to do is we are going to look at this transfer function that we derive between y and y set point and then see whether we can make some judgments about what is happening dynamically. There are reasons for control, a couple of them are servo and regulatory. There is a dynamic performance measure also that we talk about whenever we talk about controllers, which is the following. If I let us say have a certain time constant for my open loop process, which basically says if I want to change my y value, I change my input u in an open loop and then I wait for my y to get to its final value, which depends on the time constant of the process, right. So, remember we have this equation which is k over tau ps plus 1 u of s. So, if I change this, let us say I give a step to this, then this y will follow and get to some value, okay, but it is going to take its time and the time it is going to take is the time constant. Okay. So, this is the time constant. So, this is what is called an open loop time constant. Now, when we close the loop, really there is going to be a transfer function between y of s and y set point of s. Remember I said the disturbance transfer function will be modified, but still the disturbance will be an input, whereas the input transfer function will be modified, but the input will also be modified from u of s to y set point of s. Okay. So, now if I have this transfer function. Now here what I want is, let us say if I have this y set point and I suddenly change this, I do not want y to take a long time to go to the set point. So I do not want it to be like a open loop time constant, I want y to very quickly go to the set point. In Pid Controller it will go very close to the set point, but still I want this to be fast. So when I look at this, so this is what is called an open loop time constant and this is what is called a closed loop time constant. This is standard terminology that is used, but I just want you to remember that the inputs are different, right. So when we talk about an open loop time constant, we are talking about u, and when we talk about a closed loop time constant, we are talking about y set point. So that is something to keep in mind. Now if this is an open loop time constant, typically by doing control we saw that you can get steady state performance, which is how close am I to my final set point value and how much I do not deviate from my original value in the presence of disturbance and so on. But if you want a transient or a dynamic performance metric, then I might say, look, I do not want the closed loop time constant to be of the same order of the open loop time constant, because open loop time constant I have no control over, it is what the design of the process gives me. But while I talk about a closed loop time constant, basically I have had control over this. So because I am designing a controller, can I design my controller in such a way that this closed loop time constant is very small, that means whenever there is a step change it happens automatically, okay. So an analogy that I would give you is, remember the bike example we talked about. Let us say you are going at 30 kilometers, you want to increase to 50 kilometers per hour. Let us say you know what the throttle position is for 50 kilometers per hour. So you simply go to that position and then wait, right. Now if you just go to that position and wait, your bike is going to take a certain amount of time before it gets to 50 kilometers per hour. So it is going to be not instantaneous, it is going to take its own time. That is what we typically call as open loop time constant. As opposed to, imagine a case where you are simply punching in speeds for the bike and you are really not doing throttling. There is a controller which is doing throttling, which is basically you are only giving the set point and you are not manipulating, some controller is manipulating, right. So if that happens, what you would want is, if you go and press 50 as a set point, you would want the bike to get to 50 as quickly as possible. It cannot be the same rate at which it went to 50 when you simply got to the throttle position and waited, right. So that is the kind of idea we are talking about. Let us see whether a proportional controller is able to do that. So from the previous slide, again I am going to use this tau p which I have here. Now if you notice from the previous slide, this is the transfer function kkc divided by tau ps plus 1 plus kkc is y set point of s. Now I am going to do some very simple algebraic manipulation. I am going to take this 1 plus kkc outside here. So the denominator will be tau p divided by 1 plus kkc times s plus 1. Okay, all I am doing is I am taking this out. So tau ps by this plus 1 will be there, and since I am taking it out, it goes to the numerator. Okay. So ys is this. Now this is a constant, let me call it as a closed loop time constant, and now if I call this as a closed loop gain, and now if I call this as a closed loop time constant, then I will have this equation as 1 plus tau cl closed loop s. Okay. Now notice something interesting here. So in the open loop, the transfer function was y of s equal to k by tau ps plus 1 u of s, and in the closed loop it is y of s is k closed loop, just closed loop here, and this is tau p closed loop s plus 1 y sp of s. So this is also a first order transfer function, this is also a first order transfer function, except that the gains have changed and the time constants have changed. And if you look at the time constant in closed loop, if you look at this equation, this is a open loop time constant divided by this number here. Now let us go back and think about the discussion we had. We said that we want the closed loop time constants to be much smaller than the open loop time constant, which is what you see here. If you keep increasing kc more and more, then tau closed loop will be much less than tau process, right. So the closed loop time constant is going to be much less than the open loop time constant, which is something that we desire, and we see that the controller is basically able to get us that. And from a gain perspective, for this closed loop transfer function you want the gain to be 1 because y of s has to be equal to y set point of s after a while, but we notice that while the gain goes closer and closer to 1, but it is not exactly 1, that is where the offset comes in. But you can also see that from this first order form here quite easily that I have gain which is close to 1 but not really 1. So the upshot of all of this is the Pid controller works nicely in terms of reducing the closed loop time constant, making closed loop time constant much less than the open loop time constant. It is also getting the gain close to 1 but not exactly, and that is the reason why you have an offset. So again the advantage is speed of response, simplicity, however the disadvantage is an offset. Okay. So what happens if there is a step disturbance? Let us quickly summarize. So if I have a step disturbance here, then I want my output to do this, but in a Pid controller what will happen is the output might do this. So there will always be an offset between what it originally was and what happened to this. And similarly the time constant part of the disturbances, the output could do something like this or it could do something like this. Okay. So the offset cannot be got rid of, but how quickly it comes back to the close to its 0 value will be given by a corresponding time constant for the disturbance transfer function in closed loop. Okay. So which is something that that you can also work out for yourself so that you get comfortable with this material. Now let us repeat the same exercise for proportional integral controller, and the reason why you use this proportional integral controller is to get rid of one disadvantage of the proportional controller, which is the fact that a proportional controller has an offset. So in this case what we are going to try and do is see whether introducing an integration action removes this offset. Okay. So let us see what happens. So the procedure is the same, there is nothing that is complicated, we simply follow the same equations, except we are going to use the correct equation for a controller when we use a proportional integral controller. Okay. So the proportional controller had only one term Kc. In a previous lecture I had shown you that if I have a proportional integral controller, I am going to do integration of E of dt, which basically gives me Es over S. So I have this extra term and we put it in this Kc times 1 plus 1 over tau is form. Now this basically is the same, I am going to do Y S equal to Gpc divided by 1 plus Gpc, except that the C is Kc when it is a proportional controller, and when it is a proportional integral controller it is Kc times 1 plus 1 over tau is. So I substitute all of this, okay, and then I will simplify this, and then now again what I am going to do is I am going to see what happens when I have a set point change, which is a step. Okay. So I am going to again do this y set point S equal to 1 over S, okay, that will give me this times this will be 1 over S as y of S, and then now that I have a proportional integral controller, I want to see what happens to the offset. So does it really matter in terms of offset? So what I am going to do is I am going to use the final value theorem again, which is limit t tends to infinity y of t is limit s tends to 0 s y of s. So when I multiply this term by s, this s and s will get cancelled, then what will remain is this simplification. So this simplification will turn out to be this, okay. So this s and s will get cancelled from what I showed you. Now let us substitute s equal to 0. So when you substitute s equal to 0, the top term will just be 1, and when you substitute s equal to 0 here, this term will vanish because s is 0, and this term inside this is s is 0 is going to vanish. So this is going to be, since this is 1, in the numerator I have left with k Kc, in the denominator this is 0, this is 0, so I am only left with k Kc. So surprisingly or interestingly I get 1. So what this basically says is I gave a step input in my set point, and then the output also takes a final value of 1. That means the offset that was there in the Pid controller got removed in a PI controller. So this is one of the most important reasons for using a PI controller. Now this mathematics is very easy to understand, there is nothing here other than simple algebra to see why PI controller removes offset, but it takes a little bit more effort to really understand in a time domain why there would be an offset for Pid controller. and no offset for PI controller. So, I am not going to explain that here, but I will leave that as an exercise for you to really think about why from a time domain viewpoint have an offset when you have PI controller, but not so when you have a PI controller. Okay. So, this is the advantage of PI controller, that it gets rid of the offset. However, if you look at this closed loop transfer function for let us say this example, you will see that the denominator now for the closed loop transfer function becomes a quadratic equation, and you can write a solution for a quadratic equation, right. And depending on the values of tau k, kc, tau I and so on that we choose, it could happen that the term inside the root becomes negative, in which case we get complex roots for this closed loop transfer function. And remember, the minute we have complex roots for this transfer function, which we have seen before, then you could have oscillations, or you will have oscillations, because when we do this Laplace inversion, we saw that we will get these terms e power p1t, e power p2t, and if p1 is a plus ib, then I will get the cos bt and sin bt terms. Okay. So, which is why you will have oscillations that come in. So, basically while P controller removes the offset, the disadvantage is it can lead to oscillatory output behavior, but it is not that the oscillatory behavior is always going to result. By careful tuning and careful choice of the parameters of the integral action, you will always any case minimize or get rid of the offset, but by carefully choosing the tuning parameters, you can reduce the oscillatory behavior to a large extent. Nonetheless, you just want to remember that this can lead to more oscillatory behavior than the P controller. Now, it is also important to understand that it is not necessary that P controller will never introduce oscillations. That is not what we are claiming here. P controllers can also introduce oscillations. The way you have to figure out whether oscillations will be there or not is very simple. This is something that we have already discussed before in a previous lecture. All you need to do is really look at the roots of the denominator polynomial of the closed loop transfer function, and if the roots are real, then you are not going to have oscillatory behavior, but the roots are complex, then you will have oscillatory behavior. And roots can become complex even with a P controller if your transfer function is of higher order. So, in the previous example that we had, we did not see that effect because we took a first order transfer function and then we implemented a P controller. Supposing I were to have taken a higher order transfer function, I can see that even P controllers can introduce oscillations. Nonetheless, there is more oscillatory behavior in general, in layman terms, that is introduced when you have integral action. Now, we talked about P and PI. The third type of controller is PID controller. Now, most often you will see in industrial processes either P or PI controller being used. For systems where you are looking at getting a response which is very fast, ease of implementation of a controller, and you really do not care so much about offset, you would implement a P controller. But in cases where you cannot tolerate an offset, so for example, if it is related to quality, let us say you want to produce certain product of certain level of purity, in that case you might not be able to afford offset in quality parameters. So, those cases you would really ensure that you introduce a PI controller and you will tune in such a way that the oscillations are minimum. One controller which retains the removal of offset and makes the process closed loop behavior faster and removes or cuts down on oscillation is the PID controller. So, if you add another derivative action, you seem to get no offset, oscillations cut down and so on. However, PID controllers are not implemented too much in process industries at all. The reason is that, so whenever you take a derivative which is dE by dt, which is what d portion of the controller requires. Remember, we said u of t is kc et and kc over tau is integral e dt and kc tau ds dE dt. So, this is a form. So, for the derivative action you need dE dt, and you know E is basically y set point minus y. So, dE dt basically also requires you to calculate dy dt. Okay. Now, dy dt is basically computed by measurements, and typically whenever you have a sensor in a process industry, the measurements are likely to be noisy. So if you have some noisy measurement like this, so in these cases dE by dt might kind of create all kinds of robustness problems. So that is part of the reason why PID controllers are not used too much in process industry. You might argue that one could do filtering and remove the noise and still use D action, but if you are filtering, then basically you are anyway slowing down the rate at which E changes. So whenever you are filtering, you are kind of smoothing the curve, so you are losing some aspects of the speed. So unless there is a very special need, a very specific process where you need PID controller, typically industrial processes are either P or PA controller. Okay. So P controller summary, it is fast acting controller, simple, but the disadvantage is its offset. PI, its offset removal is one of the big advantages of PI controller. However, the disadvantage is that introduces oscillations. PID controller seems to remove offset, it cuts down on oscillation. However, it is not very regularly used in industrial control because of its robustness issues. Robustness issues means whenever you have measurement noise, all the differentiation can create problems for the overall control loop. Okay. So this is the basic summary of these three types of controllers, and in this lecture I showed some computations with first order transfer function. The procedure is just the same. I said there is no difference at all. You can take a second order transfer function and then play around with P, PI, PID controller computer calculations. The idea is the same. The transfer function for y set point is GPC divided by 1 plus GPC. The transfer function for the disturbance is GD divided by 1 plus GPC. And once you have GP and GD, you can choose any controller form. If choose a P controller, then C of S is simply Kc. If you choose Pi, this is Kc 1 plus 1 over tau Is, and if you choose PID, so this is Kc 1 plus 1 over tau Is plus tau ds. Okay. So all of these are transfer function forms. You just put them into those equations and then you do your basic numerator by denominator polynomial, partial fractions, inversion. You can analyze all kinds of controllers, and this is an important set of ideas when someone talks about these three types of controllers. Okay. So we end this lecture in the next lecture we will talk about how to analyze the stability of closed loop systems. The way I have been teaching is I have talked about how you analyze open loop systems using the partial fraction idea, and then I talked about stability of open loop systems by basically saying, okay, all you need to do is look at the roots of the denominator and then see what happens, and if every root is in the left half plane, then we said the open loop system is stable. And then I showed you that when you go to closed loop and you want to understand the performance of closed loop systems, you do not have to do anything differently at all. All you need to do is derive the corresponding transfer functions, and then all the open loop ideas are directly applicable to these. And from a stability viewpoint, again it is going to be just the same, because once you get these closed loop transfer functions, again you are going to look at the denominator polynomial and then see whether they are in the right half plane or left half plane, and then you are going to analyze the stability of closed loop system. So from a stability viewpoint, the ideas are the same. Only thing is the transfer function you are looking at is different, and the key connection is we have shown you how to derive the transfer function for closed loop from open loop transfer functions and the controller transfer function. So once you have this logical thought process, then analyzing stability of closed loop transfer functions or closed loop systems become very simple. So we will pick up on this idea in the next lecture and then show you some interesting concepts in terms of stability of closed loop systems. I will see you in the next lecture. Thanks.